but I would like to start. So can everybody hear me?
Yes.
And what I have uploaded, it's in fact the lectures from last week. So if you go to weekly modules, first week, it's all with my lectures. And then for today, I have uploaded already some of the things that we will talk about. And what I decided to do is before we go and speak about the various networks and then how we combine them and so forth, which is like network, and then introduce network theory. It's very important to remember or to cover briefly, for those who have not seen this before, the concept of a Fourier transform. We have seen it many times. We have not done a thorough analysis, as many people do, especially in communications, but we need to know enough of it because a lot of the functions in the network analysis, we will have to deal with them in the frequency domain. And there are some properties which are important. We are not going to go into a lot of mathematics, but we need to remember a few things. And so what I decided to do today is to just, first of all, talk about why Fourier transforms are useful. And then second, have an introduction to Fourier transforms. And if we have enough time, then we'll talk about transmission lines and lapped element models, which is mostly like a review from the past. And then equivalent circuits. Also, you know from the past how we have LC, RLCs, and so forth, all of these circuits that somehow represent a much more complex physical geometry, and those we call equivalent circuits. But we're going to get into those only if we have time. Otherwise, we're going to push this material into into Wednesday, and it's not going to take us too much time to talk about these two. So also what I did, and I want to bring your attention to that, I decided that I'm going to have answers to exercises. And this is a simple answer for exercise 1. And then I will have also answers to Zoom, to quizzes, to Top Hat quizzes. All right, and this is also a solution that I did. Primarily for those who made a mistake on this one is the difference between frequency and radial frequency. And that's what it shows here. Frequency and radial frequency do not have the same units. And that's why those of you who made a mistake made that mistake, because you consider that omega, which is a radial frequency, has the units of hertz, which is 1/2. So this one is going to explain it to you. I'm not going to spend more time on this unless you have questions, and then you come to office hours. Now, with that, if you don't have any questions that are very specific to the lectures and exercises or quizzes, I would like to start the material for today. So I will pause for a little bit to see whether you have any, and I see it on the chat. Okay, I think you're talking among yourselves, but if you have any questions, just speak out right now. Okay, I don't hear anything, so I'm moving on. So now I'm going to go back to my notes because I have graphics there, and I could not just transfer those GIFs into this is the other one. Fourier transforms usefulness. Okay, so obviously you're going to recognize something here that you have seen before. You have seen many times before, both in circuits, and I'm sure that many of you should have the fundamental classes in circuits, and also 322. In both of those, we moved from the time domain where we all live, all right? Time is an extremely important variable in our system and in our space. And we, interestingly enough, we do not design in time when it comes to circuit design. We make all of our designs in the frequency domain. And here I explain why we do that. So if you take this very simple RLC circuit, and then you write the Kirchhoff's current laws, KCL, and Kirchhoff's voltage law, KVL, you're gonna come out with equations A, B, C, and D. All right, these are the fundamental circuit equations for Ohm's law, including the capacitance and the inductance. And then if you combine these, as I show in those derivations here, in these derivations that I do there, we are coming down with one important second order differential equation. And why are we calling it a second order differential equation? Because obviously it has a second derivative with respect to time. All right. And you can solve that, but it's a complex thing to solve a second order differential equation. And that's only when we have one capacitor, one inductor. Let's assume that I was going to give you a more complex circuit that has two capacitors, two inductors. What would the order be of the differential equation, you think? Would it be
Second
two?
order. Second order.
If all of the inductors and all of the capacitors were different, what would that be?
Second order.
No. It would be a fourth order differential equation. Every time you have one reactive element, every time you have one inductor, one capacitor, then you have one specific order of a differential equation. And that is coming out of these two relations here. There is every capacitor and every inductor have one of these two. And if you put them together and the values for the inductors and the capacitors are different, then you will have a fourth order differential equation. And then, so as you increase the number of inductors and capacitors, and as you know, we have dozens, hundreds, thousands, millions of them in the existing circuits, there is no way we can solve a differential equation like that. So why did we do early? We said, we took it as granted that if we have a monochromatic signal coming here, and that is the input voltage, and let's assume that the input voltage had a frequency of omega. So for example, V of t, and then I don't know whether I gave it up here, but V of t, oops. Let's assume that V of t is V source cosine omega t. Okay, one single frequency. Then we said that by using Fourier transforms, and we did not necessarily do much with that concept of the Fourier transform, but we said that by using a Fourier transform, we can change this time domain circuit to a circuit that deals with phasors. That's how we called it at the time. And then we replaced every inductor by J omega L, which is here. And we replaced every capacitor with 1 over J omega C. Okay? And we did that. When we did this, we assumed that every J omega or omega L is equivalent to an impedance, and 1 over omega C is equivalent to omega here, and 1 over omega C is equivalent to an impedance. That's what we assumed. And then we took this simple circuit, assuming that R is an impedance, J omega L, well, J does not have units, but J omega L is like in the form of an impedance, 1 over J omega C in the form of an impedance. And then we solved this circuit here as if it were a circuit with only impedances, like resistors of some sort. Now there are resistors, and then there are imaginary, say, imaginary components, like the J omega L has a J in front of it, but we treated it as an impedance, as a resistor. And the 1 over J omega C has a 1 over J, but we treated it as a resistor too. And so if you take all of the familiar then formulas we have, you find an expression for V, all right? And this V, as a matter of fact, this is V sub S of V, is exactly the V you see here, V sub S, let's put it here, V sub S. And we found, therefore, an expression for V sub S in the phasor domain, and where we call that V sub S the phasor. All right, for the of V of t. So if I were, without getting more into the fundamentals that we covered into 322 or other previous circuit courses, I would say that we have learned on how to take this time domain circuit and move it to the phasor domain, and then solve in the phasor domain and find V sub S, which is then is the phasor of V of t. And how do we then capture, and as a matter of fact, to be careful here, I will use a small of this one. I'll show you why. Okay, and then how are we going to get from here V of t? V of t is nothing else, according to what we've learned before, but the real part of V of s e to the j omega t. Okay, so then if we replace here V of s but by whatever we find up here, if we take this and we replace it here, all right, so we take this one. And replace it there, then we're going to find V of t in the time domain. And so then we solved a problem that was fairly complex in the time domain. We solved it in a very easy way. Do you recall this material? Have you seen it before? Okay, I think somebody say yes. All right. Hopefully you have seen it before, because this is fundamental. For those of you who don't remember this material, I would suggest that you go back and review it. Okay, so this is why Fourier transforms are useful. All right, now that we have seen why we need a Fourier transform, let's talk a little bit about what is a Fourier transform. Let's get a little more in depth. And the reason we want to do that is not so much because we will have to solve circuits. Always we solve circuits in the phasor domain, but we have to understand Fourier transforms because you will see that a lot of the devices that we are going to design, they will have different performances at different frequencies. So they will have some kind of frequency response.
Dr. Katehi?
Yes.
Would you mind returning to the last page?
Yes. Let me do that. This one.
I just want to notify something.
Yes.
Give me 1 minute. 1 minute. So VS is phasor. It should be amplitude, right? Magnitude.
Yes. But we call it a phasor the way it is here. And it's not a magnitude, it is a phasor. Little vs is the magnitude. You see the little b up here?
Oh, so I'll make an annotation and then erase. Oh, sorry. Okay. So this one, the one inside the V of t is little v. And the one above is big V.
So this one is little v.
Right.
This is capital V.
Yes.
Okay. The capital.
Oh, this is little v.
What is little v? The little v is up here. Here. Little v is here.
Oh, so this is little. That is little.
Yeah, that's little. And that and this is capital. And this is the phasor. Phasor.
Which one? Oh, this big V is phasor.
Yes. Okay.
Okay, so small v is magnitude.
Amplitude. Yeah.
Oh, I see.
Okay. Let us, is it clear with everybody else? All right. I will put those, I will upload those after our lecture, since I will have notes that might be useful. So let me then go to Fourier transforms. So then we said, as I said, it's okay to do the transition from the time domain to the frequency domain using the concept of phasors. But there are two things then that we will have to keep in mind, that as we design like filters, amplifiers, mixers, they have a fairly complex performance in the frequency domain. So filters, for example, will be linear, amplifiers and mixers will be nonlinear. And then it becomes very difficult then to be able to keep the simplicity of the solution just by using phasors. We need to understand more about what happens when we transition from time domain to frequency domain. So that is number one. Number two, when we are going to talk about modulation of signals, and this is important because you remember I said you need a carrier to take it audio signal from one end of a state to another end of the state so two people can speak on the phone, on their wireless phones. You need a carrier. And the signal, the audio signal, is not just one frequency. It's going to be multiple frequencies. So you have to take that and then modulate the carrier. So now your input signal into your system is going to be fairly complex. It's not going to be one harmonic. It's going to be very many harmonics. And as a matter of fact, when you modulate them, especially if you modulate them with bits like zeros and ones, it will be even more complex. So it is critical to understand what is happening at some level when we transform our circuits from the space that incorporates time, and that's where we live, to a new space where time now gets eliminated and then is replaced by frequency. And that's a new space. We don't live in that space. We just made it because it helps us design circuits. Okay, so when we try to do a Fourier transform, for a simple signal, which is here the cosine, okay, that one, has an amplitude of V naught, has a frequency omega naught. Now we know that this only has one frequency. So I don't have to apply anything complex to find out that in the frequency domain, I would have practically one frequency, omega naught, and it's here. All right. Then an important thing to keep in mind is the following. As the signal moves, changes with time, then there is, because it's changes as a cosine of omega naught t, that omega naught t creates, as time goes by, creates a phase for the signal. Okay, so in fact, you see it from here. So the blue one shows the phase. It starts at this point here, and then it moves around to, like, in fact, it moves in this direction, counterclockwise. And that, as a matter of fact, shows how when your signal changes from +1, all right, when you are right at this point here, oops. This is the second time that happened, okay. When you are right at this point, at where the x starts, and then you start at +1 for the cosine function, you start at 0 for the sine function. So you start at +1 for the cosine, you start at 0 for the sine function. And then as time goes by, the phase of the signal changes. All right, now, why is that important? Because
It's 2 o'clock.
I can get the same signal also by creating a different type of a rotation. So if I go the opposite way, and we are going to come back again, but I will write it here. If I have another rotation that goes clockwise, then in that new rotation, which corresponds to a negative frequency, it does not really, the negative frequencies do not exist, but a negative frequency here would mean a different rotation, a different change of the phase of your signal. Then practically your signal will be identical. The only thing is that as time goes by, the phase changes in a different way. So it's as if the phase here changes in the counter, in the clockwise, and that will be equivalent to a minus omega naught frequency. So this is clockwise when the phase changes in that way. And when the phase changes in the counterclockwise, that corresponds to positive. So while in reality, there are no counterclockwise, while in the reality, there are not the negative frequencies. A negative frequency may just imply the direction of the rotation of the change of the phase. So because of that, because the two rotations give rise to the same signal, then we say that one signal like this, which is a cosine of omega t, omega 0 t, has two frequencies mathematically. One which corresponds to a phase change in the counterclockwise rotation, the plus omega naught, and the minus omega naught, which is a similar signal, but its phase changes the opposite way with a clockwise rotation. So this, I wanted to say that because you will see negative frequencies, but, and then you will get confused. You will say, what does a negative frequency mean? So physically, it means just the change of the rotation of the change, the way the phase of a signal changes. Okay, now here you see one signal to the left that changes in the counter. Always here we show the counter clockwise because that gives us a positive frequency, but the identical will be for the clockwise. Okay, so you have that. When you take two signals at different frequencies, you get here the result on the right. And then it's an easy thing to superimpose. I mean, if you use this circle, that kind of, you see how they change and how they're, as the phase changes and the orientation of the two signals, how they combine to give this green one. So from two frequencies that each one of them is like a cosine function, and practically each one of them have the same amplitude, the fact that they have a different phase, they start at different times, when they superimpose, they give this green signal. So that is exactly what happens when two frequencies come together and superimpose with different phases. All right, so that is something visually to see. Why is that now superposition of multiple frequencies important? Because if from two frequencies I go to three frequencies, then my superposition, you see in the beginning here, the superposition gave something like this. Something like that, okay? The superposition here, when you go from 2 to 3, it gives something similar, but not exactly the same. It gives us a very particular shape that looks more like a positive and a negative pulse. And then I can go to 6 frequencies that I superimpose, and I can get this one. And that's very interesting to realize, because what is happening is I can create signals by superimposing multiple monochromatic waves. And that is extremely important, because in reality, there will be all of these frequencies in your space. And they will be like, for example, this phone works in 5G, but has a bandwidth around, it's not exactly sharp 5G, 5 gigahertz it's working on. It's working around 5 gigahertz by a very particular bandwidth. So there are a lot of these frequencies that are utilized to give signals which in time domain are time complex. And in addition to that, after they're modulated, and there are different ways to modulate these, each one of them are carrier signals, all right? I use them as carrier signals. So I can use not only one carrier signal, which is 5 gigahertz, I can use multiples, and then I can modulate each one of them separately, and then superimpose them. And then this way I have the capacity to put many more bits, much more data over a frequency, small frequency range, as opposed to using only one carrier. So if, for example, using one carrier, I could transfer an X number of bits. By using 3 carriers, I can transfer 3 times that. By using 5 carriers, I can transfer 5 times that. All right, and I can do all of these within a narrow bandwidth. So I don't need to have separate systems, each one of them operating for each carrier. But if all of the carriers are very, very close, 5 gigahertz, then I can have one system that can receive all of these carriers, and each one of them is modulated. So if I demodulate, if I then do an inverse transform, and I can, or I do a transform, and I can get all of these frequencies separately and then demodulate them, and then combine all of the data, I have a lot more information that I was able to send. Does that make sense to you, the way I described it?
Yes, I had a question about the 2 frequencies though.
Yes.
So if, let's say if the red and blue frequencies had opposite phases, would they cancel each other out?
They cannot cancel each other all the time, unless you have a clockwise and a counterclockwise at the same time, and nobody will do that.
Okay, so as long as they're both counterclockwise or clockwise, they won't cancel out.
Exactly.
Okay, thank you.
They will cancel only over specific points, but not throughout. So we will always use counterclockwise signals, but I just wanted to explain that the negative frequencies that you see, they have a meaning. There is a physical meaning to it. It's not just a mathematical byproduct or mathematical junk, if you like. They have a physical meaning. It's just that we always use counterclockwise signals, and then we superimpose those. Okay. I have another question that says, to modify, change the signal, like if you wanted to see information, something. I think I can see you guys talking to each other, which is good. But if you want to ask a very specific question to me, please speak out, because otherwise there is so much going. So I will leave the chat for you to talk to each other, and then with me, you just ask me directly, okay? Now, what I would like to do next is to remind you a little bit of the definition, mathematical definition of the Fourier transform. And what that really says is the following. If I have, let's start with equation 2 here. It says that if I have a signal in time domain, then practically, other if it's a harmonic, when I have only 2 frequencies, and that can come out of this definition. In reality, a complex signal will probably have a continuum of frequencies. And so if I want to consider accurately this continuum that shows out of the minus infinity, plus infinity here, and obviously, you see here you have a continuum of frequencies. If I wanted to capture this signal, then I have to sum up, superimpose all of these frequencies. Or I could say that a signal here, so the reverse of this, will say the following, that a signal v of t has a continuum of frequencies. And so if we want to find the Fourier transform v of omega for this signal v of t, we will have to apply this integral. And if we know all of this v of omega, and we want to find the signal that they contribute to, then we have to use this inverse, what we call inverse Fourier transform. All of these are definitions. Fourier was the first one who introduced that, so he had the privilege of defining everything. So what is the Fourier transform? What is the inverse? Now, with this in mind, we are going to then continue here and demonstrate, it's okay, and demonstrate that if you use 1 and 2 for a cosine for one harmonic, you get the 2 frequencies. And I have this here, but the only, and I don't know how many of you have seen these derivations. How many of you have seen anything like this? Okay, how many of you have not seen anything like this? You can raise your hands. I don't know whether you know how to find it or speak out. So since I don't hear anything at this point, I will assume that you have seen that. So practically what I told you.
Dr. Kateli?
Yes.
Which one are you talking about? Are you talking about that cosine?
Yes.
That's, well, the split of cosine functions into polar forms were learned in 314. I remember that.
Okay, have you seen a proof like this?
Not sure.
Okay. I would suggest that you read my notes very carefully, okay? And then ask me questions about that. But if you follow the notes and the definition of what we call the delta function, have you seen the delta function? Do you know what a delta function is? I think yes.
Yes.
Okay, so then for those of you who have not seen exactly the proof, please come back to review it. Now, I did a proof for something simple, which is the harmonic signal. But if you go and apply those things to more complex functions like a pulse, let's assume that your input is a bit, 1 bit. 1 bit is a pulse, all right, that has a value of 1 and has a width. Then in the frequency domain, that 1 bit is going to give you something like that if it's centered. Now, of course, mathematically at time t equals 0. Now, t equals 0, you cannot have that centered around t equals 0 when you start, because that means that you lose half of your pulse already. All right, the moment you generate it and then leaves your system, is going to be t equals 0. So usually we have a pulse that looks like this. In reality, when we generate a bit, it's going to look like this. And in fact, it's not going to start at, if it's a trail of bits, one of them is going to start at t equals 0 and everything else is going to follow. Okay. Now, if you take the Fourier transform, as you know from phasors, so a Fourier transform and a phasor are practically the same thing. The difference is that the Fourier transform is for a general function, and the name phasor goes to only one monochromatic function, okay? So practically a phasor is nothing else than the Fourier transform of a monochromatic function, considering the counterclockwise kind of movement. All right. What do we know about phasors? That phasors are complex functions. They have magnitude and they have phase. All right. So all of the Fourier transforms are complex functions. They have a magnitude and a phase, or they have a real and an imaginary part. So here, if you move, that the interesting thing in this particular case is that mathematically, if your pulse is centered around t equals 0, then your real and imaginary part of your Fourier transform are the same, and they are called the zinc function. The zinc function is sine x over x. Okay? And the zinc function is defined at x equals 0 and has a magnitude of 1. Is 1 when x goes to 0. All right? So if your pulse starts at t equals 0, then the Fourier transform is not going to be, the two functions are going to be different. Of course, they're not going to be both a zinc function, but they're going to have a real part that looks like a zinc function and an imaginary part that looks like a similar but flipped over the center. So it's 0 at the center. Okay. Now, why I'm saying that, I'm interested mostly in pulses, and then I will probably stick for now with this pulse, even if our reference point is at t equals 0. And then we said that if you take a pulse and you go to the frequency domain, either you're going to see the real and the imaginary part, because the Fourier transforms are complex functions. They have a real and an imaginary part, or you're going to see it in the form of magnitude and phase. Okay, so if we were to take the pulse function and look at the magnitude and phase, that's how they look. So when we go away from the real and imaginary to magnitude and phase, it's better in our design. And you will see that in filters. When we do filters, we're not going to talk about the real part of the transform of the filter and the imaginary part. we are going to talk about the performance of the filter only in its magnitude, which is this one. All right. And then if you want to be very sophisticated in your design, you're not going to only design the filter for the magnitude, but you're going to design the filter also for phase. And what do you think? Let's now think a little bit. Assume you know the concept of a filter, all right? So you have a signal and goes through this device that we call a filter and keeps some frequencies and filters other frequencies. That's where the name comes from. All right, but we want to keep the integrity of the signal. We don't want to lose information out of the signal when we filter some unwanted frequencies. So let me ask you a question, just from on the conceptual part of this. If I were to design an ideal filter, optimal, what kind of, in the frequency domain, and let's assume that I want to keep the low frequencies only. What kind of amplitude would I like to have of the filter? How would I like the response of the filter to look in the frequency domain? And how would I like its phase? The response could be like this, the one that I have here, right? If I push the side lobes, if I call side lobes these ones, let me here, go to this one, go to this one. Okay, I call side lobes this one because they're small. Ideally, I don't want them, but they're there. The main lobe is this one. The main lobe is this. I like the main lobe. This is a low pass filter, for example. I can consider that as a low pass filter. Low pass because everything goes through if I were to use that as a filter. But then what would I like that kind of phase here? What kind of phase would I like in an ideal filter?
There to be no, for phase to be constant.
Yes, we would like the phase to be constant. What it will be, so, you know, it does not change the information in the phase of the incoming signal. What will be the next best other than constant?
To minimize the change, keep it very small.
Yes. Would be linear, because then I can extract.
Yes.
All right, so linear is predictable. If I know how much it is in two frequencies, I know how much it's going to be in the rest of the frequency. I can extract it. I don't want to add more phase into whatever comes through my filter. So in a receiver, you need to keep in mind the following. Whatever I do to my incoming signal, I do not want to lose its information. Because if I add garbage into the signal, then I lose the information. So in everything we do, we want to be accurate and know exactly what we do to the amplitude of the signal, how we amplify it. We need to amplify all the frequencies if possible the same way, all right? We will need to not change the phase between the frequencies. If we change the phase, it has to be in a way that can help us extract the what we do to it as it goes through. So in an ideal filter, we want this to be a straight line. If that were a filter with this kind of performance, this kind of phase is not good. So this is some of the things that we have to keep in mind. In any case, I just wanted to say that in this, as we are coming now to the end of this class and I have something to give you, I have supplemental reading for you. When you have time, I want you, I got also the book. I told this book is from Darabi's book, this copy, this part, and is exactly what I told you. And they give you a simple example. We will do this a little later. If you want to read a little bit this example, it shows exactly what happens when you have a sawtooth generator, and then you have a smooth signal that goes through, and what happens to it when they go through a comparator. For those of you who had circuits, you would probably be able to read that if this is something that at some point later will come back to it. But I just left it there. This is supplemental reading, but please make sure that you read everything that we covered up until today. So we now, with this, I have the following that I would like to give you from a campus. So if we go to our class, if we go here, oops. Okay. Then go to Top Hat. And if you go to the Top Hat, I will give you this problem here. And I will assign it to you, and I would like you to finish it in 5 minutes. This is a circuit you have seen. It's an RC. And it says, consider the series RC circuit shown. I left an N in the figure. Assume that V in has a DC component, V in. Will the output voltage include a DC component? Yes, no, or it depends. 5 minutes, okay? I will count the time for 5 minutes, and then you will be able to go. Thank you. I'll assign it now. I'll assign it, and I don't want you to see exactly what is happening, so I will move out because I share the same screen with you, and if I look at it, you are looking at it. So 5 minutes.
Dr. Katehi? Yes. How can I join the course on Top Hat?
Have you signed up?
I haven't joined yet.
Okay. Then you need to talk to me through office hours, during office hours.
I'll try here.
I think it's time. I will turn it off. Okay. So it's been 5 minutes. Unassign. Okay, so you can see here my screen. The correct answer is yes. So for those of you who have difficulty, 9 plus 4 individuals have difficulty, I would suggest that it's extremely important to review this material. It's things that were covered in 332. It's a good opportunity to review it now, because as we move forward, we're only going to build on it. So if that presents some difficulties for you, then it's going to be much harder later. So I'm going to put the solution on the web sometime tomorrow, but I think it's going to be extremely important, and I will do this as a review so you can see, I believe, your grades. It will be extremely important for you to, for those of you who had difficulties, to review the material. Just go back to your previous notes from your previous class, your book, go on the web. There are a lot of resources nowadays, okay? So thank you. And for those of you who wanna come to my office hours, I'll be available. There is one student who wants to see me, so I'll stick around for a few more minutes. For anybody who wants to speak to me, there is one who wants to speak to me right now.
Professor, I have a question.
Yes.
It's unrelated to the lecture. I emailed you Friday evening, but I didn't get a response. I was just wondering if you got that.
I might have missed it. So could you send it to me again?
Yes, I'll resend it.
Okay, thank you. I think I definitely missed it because I was receiving, because this a number of emails, as you can imagine, in the beginning of the class. So I will definitely respond to you.
Dr. Dehi, when should we get our, because I know that we have to have our teams meet you in office hours. When should we get that, or when is the due date for that, for lack of better words?
Get office hours or get the teams. I mean, I think everybody has been right now. I had a couple of people who wanted to, if you feel comfortable with your team, you don't want to make any changes. I mean, anytime right now, it's good to start connecting with me. So it's not just about the particular work, but I need to get to meet the students too.
Okay.
So that's the only opportunity to meet students through office hours.
Okay.
Okay.
Cool. Thank you.
Sure.
Professor,
yes.
If we wanted to change teams, should we just email you the people that we wanted on the new team, or is there a process for that?
Yes, you can email me and tell me what kind of changes you would like to see happen, and give me some reasons if possible.
Okay, and is there a due date or just as soon as possible?
No, do it as soon as possible, because the teams, the sooner we finalize the teams, the better off it's going to be for everyone.
Okay, thank you, Professor.
Professor, I have a question about the top hat.
Yes.
Would the answer be opposite if the if the resistor and the capacitor were flipped?
Yes.
Okay, thank you.
Sure.
Professor, I have a quick question.
Yes.
For the transmission line material that's covered on the first homework, I think you mentioned earlier on you'll be covering part of that in class as a review, but is there any way that you could post the 322 lecture notes for that material? Just because I took the class a while ago and all the notes were on paper, so I don't know if I have the material.
I can do that. I need to find out. I have this available from my class 322. So let me see. I'll put them probably some review notes. And yeah, I'll do that. If I cannot do this immediately, but I will do it if over the weekend, if it's okay with you.
Thank you. That works great. Thank you so much.
Okay.
Professor, I forwarded the email to you. I was just wondering if you got it.
Okay, let me see.
Your email address is just your last name at Tamu, right?
Yes, yes, I got it.
Okay, thank you.
Yes, I know what, yes. I got it now, I know. Yes, I saw your email, but I have not made the decision yet, that's why.
Oh, okay.
I will probably extend it. If I am to extend it beyond the class, I will extend it for about 6 hours. So it's not gonna be 6 p.m. I will make, thank you. Remind me if I don't make an announcement on Wednesday about that, could you remind me?
Yes, at the end of class, I'll bring it up if you haven't said anything.
So it's gonna be like from 3, if I keep it open, it's gonna be until 9 p.m.
Okay, thank you.
You're welcome.
Professor, I emailed you earlier about the homework.
Hi, Max. How are you?
I'm doing good. Yeah, I was kind of waiting for people to get their quick questions out of the way.
So, yeah, you asked me a very good question about this, and let me get to that problem so we can talk specifics. You know, eCampus had all kinds of problems today, and I'm losing connection all the time, both Zoom and that. So let me go back.
Yeah, I noticed that too. It was down for me for about an hour, but I did finally manage to email or to download the homework.
Yeah, it is. It has been, and they said Zoom had problems in the whole country today. I guess all the universities are starting or something. And then eCampus had problems today for me too. So now I'm just trying to get on it again. Okay, got me on. I don't have to. All right, let me do that. I'm going to homework. Homework. Oops, homework. All right, so let me then do one more thing. Here, capture, join the meeting. Even that's kind of interesting. Okay, let me change computers first. Since I have you see this one. Okay, let me see. 1 second. Okay, let me see. Share. Hmm. 1 second. I need to get my. I'll try to find the homework. Yeah, Zoom went down. All right, so. Okay, do you see that now?
Yeah, I see the homework on the screen.
Okay, perfect. So your question was what happens with the lines and whether they're grounded or anything.
Yeah, correct. So my initial thought was that the ground symbol implies that both for coax, for example, the shield and the center conductor are grounded together, so it's treated as a short circuit.
Yes. And what happens then that's for the yellow, all right? For the one that we indicate as yellow here.
Yes, correct.
Yeah, for this one, what do you think is happening?
Well, it has the 50 ohm purely real load impedance, so because it acts as a quarter wave transformer, I can transform that 50 ohm to whatever I need at the input. I just need the input to be purely real, so I use the yellow box to create the negative J40 at admittance, and then I can transfer that to 50 ohms.
Yeah. So you need to remember that always like if it's a coaxial, the outside conductor, if it's a microstrip, the ground are all grounded, all right? Even if we show them when you have a more complex representation of the ideal transmission line, that you always show not only like in this schematic form, but you show the two wires, like into wire form, you always, the one is grounded. Okay, you need to remember that. So obviously here you show it in schematic form, and the ground means that both are grounded, so you have a short. And in the yellow, and in the blue means that one is connected to the load and the other one is grounded. So the load shows at the end of the Z01.
Excellent. Yeah, I just, I guess wanted to get some clarification on that, make sure that I'm on the right page there.
Okay, that sounds good. Anything else? Any other questions?
Will our exam be online? Or will it be, or will you reserve a room for us to take the exam?
No, everything is gonna be online in this class.
Okay.
And the exam is gonna be like online, yeah, whatever. We did it, however we did it last fall.
Okay. I wasn't here last fall, so
yeah.
I was on an internship. So.
You were in internship. Yes, it's gonna be online.
Okay, we'll be on eCampus or?
Yes, eCampus.
Okay, all right.
Hopefully eCampus is gonna work, but I will have, in case that something happens, we are gonna be prepared, but it's gonna be online, you're gonna receive it online, you're gonna solve it, and then you're gonna upload it as a PDF, the solutions.
Okay, all right. How long do you think will be given to?
As long as it says on the syllabus, and the time I think is from 11, whatever it is, it's in the academic calendar. It's gonna be.
Okay, it's the same time as they usually allow us. All right, all right.
Yes. We're not gonna change those, obviously, because they will create huge conflicts for all students.
Okay. All right. Thanks.
Sure.
I have another question about submitting work.
Yes.
So two things, I guess. First of all, are you okay with us solving it like in application like OneNote or something like that digitally, and then submitting that as a PDF?
Of course. I mean, you know, you can write it, you can do it on OneNote, you can do it on anything else, as long as you can even take a picture, as long as you eventually make it a PDF.
Okay, that kind of answers my other question. I'm just going to ask it just to be sure. You say that you'd prefer us to use Tiny Scanner?
No. I just gave that as an example. I realized that now may not be free. When I downloaded it was free for me. So, but there are all kinds of other applications that allow you to do to take a scan, to scan a document. Because a lot of times students in the past gave me pictures, and if the picture is not well taken and it's fuzzy, I will not be able to read the details. You know, it's so in some previous classes. That's why I want everything to be in a PDF. However you create a PDF, you know, I don't necessarily want a Tiny Scanner. That's what I have.
Okay, so as long as we can submit a legible PDF, everything's all right. And then for exams, can we use OneNote too, or do we have to?
Of course. Yes, I'm using OneNote for whatever I do by hand, practically. Yeah.
Okay, I just wanted to clarify that before I get all set up to do something, and then you know, it's not going to work out.
No, absolutely.
Awesome. Well, thank you so much. I appreciate you taking the time to go over the homework with me a little bit, and I'll see you in class.